So back in 2007, I think it was, I was at a workshop in Haines Junction, Yukon. And this climatologist, Tim Chittle from Colorado, was speaking. And he said, you know, yeah, there's lots of uncertainty and information and a variety of models that we use, but one thing we can be certain is that climate change changes everything. Right? He's right. And so I started thinking more reflectively about the implications of that. And then shortly thereafter, I returned to British Columbia, and I was talking with some other conservationists and land use planners, and realized that we had an opportunity to try and address climate change in land use planning in northern British Columbia, because up until then, there have been lots of land use plans developed in the province with great effort, over a period of more than 5 years, dozens of them, and none of them mentioned climate change. It just wasn't part of the picture. But we had the opportunity in Atlin-Taku to get in on the ground floor, so to speak, of land use planning. And Atlin-Taku is the area will be right here. And then shortly after that, then we had the idea to reassess the existing land use plan in the Muskwa-Kechika management area. In the northern area of Yukon. They already had a land use plan that resulted in lots of protected areas as well as special management areas and industrial zones of opportunity, but they too had not considered climate change. So we thought, well, let's reassess what they came up with a few years ago. And also, in both cases, there was a underlying so-called conservation area design that had been developed by the Round River people and in Atlin-Taku in collaboration with the local First Nation, the Taku River Tlingit. So these two conservation area designs were also part of the mix, and they provided some useful information, especially about habitat quality and suitability for a suite of focal species. So we were trying to figure out, well, what can we do differently in these areas, well, especially in Atlin-Taku, because we had the opportunity to get in on the ground floor. And I'm a plant guy, and I always will be. But I have the adaptive capacity to become a forester in order to make a living. And Rosamond and I were also able to migrate to a place in northwestern BC, Smithers, Paltry Valley, for the quality of life, and a place where there was still a nurturing matrix. So we had a good life there. And as part of my life as a forester, I spent decades doing ecological classification, describing vegetation and soils all over the place. years and years of field work, and most of that was spent in the company of earth scientists, soil scientists, and geomorphologists, especially. And again, unfortunately, I have the adaptive capacity to absorb some of what they were thinking and the way they were reading the landscape as part of our job. We'd sit there talking for quite a while about the soil pit and the vegetation and what that was telling us. So I got together with a handful of people, and we talked about what we might try in the Atlin-Taku, realizing that the traditional conservation approaches, as I mentioned in this background thing, why enduring features, the traditional approaches, the traditional conservation approaches dealt with protected areas and connectivity and minimum viable populations and that sort of thing. But without thinking about the changing climate, it couldn't really comprehend the major transformations in biodiversity on land and in water and across all levels. I mean, gene, species, ecosystems, and the interaction among them. You're just missing the boat in that respect. The upheaval. If you ever read those books from 30 or 40 years ago, Earth in Upheaval or World in Collision by this guy, Emmanuel Balakowski. A bit flaky, but anyway. Those were the kind of apocalyptic thoughts I was having. And we also realized that most of the current approaches for addressing climate change and conservation planning are focusing on projections of future suitable habitat for individual species based on climate envelope modeling, on securing areas projected to be future refuge for species, and on maintaining or strengthening connectivity in general. And as I say, those are all worthy conservation efforts, but they're challenged by large uncertainties and dicey assumptions about climate models, greenhouse gas emission scenarios, species behavior and dispersal, future habitat conditions, and the sheer unpredictability of biological response to a rapidly changing climate. So we thought, what about taking a look at the geophysical environment? And that had been done a few places, especially in the eastern U.S. by some ecologists. And there just happened to be a fellow who worked with Mark Anderson, I think his name was, in the Northeast. This fellow's name is Greg Kim, and at the time he was working for EcoTrust Canada. And he said, well, I know about this geophysical model, this enduring features model. Let's try it as an alternative or complementary approach to develop a conservation plan. Relying on physical features, on the habitat elements that will persist more or less unaltered as climate changes. And the assumption in this approach is that physical habitat heterogeneity drives species richness, that biodiversity is in large part a consequence of geophysical diversity. And I'm talking about long time periods here. the true broad concept of biological diversity, not just species diversity. So if you bought that assumption, let me ask you how you would start to partition a theoretical cross-section of the Northwest Boreal region from southwest to northeast, coming from the coast up over the big mountain, flattening out, and rising again to another mountain range. So, if you wanted to partition that landscape into physical units that have ecological meaning, how would you start? Okay. Elevation, aspect, what else makes up the puzzle? Yeah. So, that's a good start. Topography, elevation, slope, aspect. And you can do that with digital elevation model and those things like this. And the data is digital. And of course, here's where I couldn't do this myself. We need a GIS jockey, like Greg Kent. He knows where to get the digital information and knows how to play with it. What else makes up the geophysical environment that has ecological implications? I mean, biota occur on that. Soil? Water courses are very important. Let's start with the soil. Where does the soil derive from? Local material. Yeah. Parent materials? Parent materials, yeah. Okay. And where do they come from? Bedrock. Something sedimentary? Yeah. What's that a class of? There's different kinds of deposits. So that would be like landforms. And what kind of superficial deposits do we have? Sedimentary is one. We have colluvial, that's the stuff that moves down slope through gravity, the bedrock principle. And then there's moraine, rock by the glaciers. There's other stuff like lacustrine, trouble lakes, and there's different kinds of lacustrine. And there's eolian. What about along flowing water? That's for those are all different kinds of landforms that contribute to the parent material, which contributes to the soil. And the bedrock, of course, as it breaks down, also provides parent material directly, like on a colluvial slope, or it can be transmitted, moved by ice or water. Now we categorize of aquatic enduring features, what would you include there? What does that mean, Don?
Flowing or streams?
Oh, streams and lakes. On this diagram, this is a big lake in the middle of the coastal ranges. Could be boundary ranges. A big lake like Atlin Lake. And this could be the Taku River. A smaller stream here. We can't fiddle around with the really small stuff. What about sort of moisture receiving sites or accumulating sites on a plateau like that? That isn't open water. Wetland. In some respects, that's not purely physical, right? Because you identify it by surface vegetation. But just thinking of the landform, where there's a depression and it's wet, and especially if it's got organic soil, it's probably going to persist as a wetland for some time. If it's big enough. So you can't worry about all those little steps. If you've got a big wetland complex, I would identify it as an enduring feature. And there could be another one, some of those back swamps along the river. This is a river. This represents some dunes for aeolian material. And of course, in this region, there's big areas of the lowest aeolian spots. So it's a really significant landform. And under the landform category, there's an important subunit of moving with nasal things like esters and chains and fluid outwash, and could occur on a surface like that. We've got topography, bedrock geology. Bedrock geology, well, there's all sorts of types of bedrock. I can't go into too much detail about them, but the information is this. You can group them into general categories like igneous, intrusive, metamorphic, sedimentary, ultramafic, or serpentine, volcanic. That's a good place to start. We've got the landforms, we have soil. I kind of with soil and permafrost, a couple of edaphic components that I wouldn't call true enduring features because soil actually can change faster than we realize. And the permafrost is melting already. On the other hand, it's not going to disappear overnight. It's been being in the landscape for a long time, at a greater depth maybe. But if you have information about its occurrence, I would include it in the enduring feature model. And much of Canada, anyway, we don't really know why permafrost. Areas are mapped as irregular permafrost, high potential for permafrost. That's a good start. What about the cross section? What if you were looking down from a plane or at a landscape image or a Google Earth or something? Once again, you're trying to partition this region. And there's an ecological, meaningful physical need. Okay, so what? Who is that? What is that? What's in the middle? What's that? What I'm part of that? A basin. There's another. Another basin down here. That's the Yard basin. The Washington Lake thing around here. Now those are both basins, but they're very different. Not only in terms of their land cover surface, but also just the topography and the type of soil. And then you have here the mountain ranges. Okay, you've got the Alaska Range and American Mountains, Arizona Mountains, Canada Mountains. You know, they're all mountains. They've got a lot of fun. Not seen physically, but different origins, technically, different bedrock. And even Boreal biota, most of the species are widespread. A lot of them circumboreal. And so the species that might occur on those different physiographic units are the same. Nonetheless, those physiographic units, like the basin that Fairbanks is in and the basin, the Yard basin, for those different mountain ranges, they have a lot of the same species, but the pattern of ecosystems will differ. The pattern of landscape, of ecosystems across the landscape, just the drainage patterns differ. And in some cases, if the geology is really different, well, then you get quite a different assemblage of species, too, like limestone versus granite. So, physiography would be physiographic units. Would be another component of enduring features model. So we've got topography, bedrock geology, physiographic units, and there's three main types of those general types: mountains, plateaus, and basins. Superficial geology or landforms, soils and permafrost in parentheses, and the aquatic system. as I said, the sort of traditional conservation biology approach, or one that's been widely used in the West anyway, is then coarse filter, fine filter along 3 streams in each case. The abiotic elements, the biotic, and then the biotic elements, including species and ecosystems, and communities and ecosystems, and then species, individual species. What moves it forward, Amanda?
Down arrow and the right arrow. Okay, now you see how to use arrow.
Okay. And this just summarizes what we were going over there on the whiteboard. Geophysical features that will not change much as climate change. I mean, everything's going to change, especially given geological time. But the mountains and rivers and big lakes will remain. The marina blankets and the escar complexes like this one here will stay more or less as they are, barring some big landslide or something. And you can get this, the information exists. These are this is the generalized bedrock geology for part of British Columbia. From Linkages and Jerusalem up to sedimentary limestone. And one thing about the Northwest Boreal region is that it's incredibly complex in terms of bedrock because of what's happened in its origin, all the continental drift and subducting and mashing together and metamorphosing, and then the more recent volcanism. The physiographic regions also exist. These are pretty general ones like the Cassia, and I'm going to look them up and bring up to the middle of the boundary ranges are part of the coastal Muskwa regions and the northern Canadian Rockies. Parallel classifications exist for the Yukon and for Alaska. I mean, they've been around for 40 years, probably. In the case of the Muskwa-Kechika, then, we divided the study area physiographically into the provinces, the bigger chunks here on the left, and then there were sub-provinces. So the Rocky Mountains is a big physiographic province, goes all the way down to Canadian Rockies, all the way down to Glacier National Park. This northern chunk of them are called the Muskwa Ranges. The Cassia Mountains plus several different ranges within them that are distinct enough physically that we thought it was worthwhile splitting them out. And as I was saying, they're all mountains, but these are really different physical environments, and the biota responds to it in very different ways, whether it's the northern Rockies or the intrusive igneous Englishman Range in the southern Yukon, the boundary ranges, or the Horse Ranch Range, which is sort of unique geologically and physiographically. And then you can also get the landform information, again, from some generalized mapping. This tells the alluvial, glacial, fluvial, lacustrine, and so forth. What you're trying to get at is partitioning what happens on hill slopes with alluvial action and all the other kinds of deposits are laid down by glaciers or wind or water. Oftentimes the landforms haven't been mapped to the level of detail I find useful, but at least you can do something that we call macro landforms. I'll get into that in a bit. So the sequence of developing the model was to create 9 classes of elevation and incorporate aspect with that, aspect and slope with that, and create a digital elevation model. And in the case of slope, we just used basically southern and southwestern southeast, a warmer aspect and a colder one. You could make it finer than that, but we try to keep it simple. The substrate classes, that's bedrock geology, the landforms, what we were talking about.
Pardon the interruption. Your conference is less than 3 participants at this time.
And then we combine them into a single map of enduring features. There were essentially over 2,000 combinations. 1,600 of them actually occurred. This is Atlin-Taku and Muskwa-Kechika. We can have a look at this map that shows in better detail the pointillist nature of this kind of a map. And because we didn't have sufficiently detailed landform information for everywhere in the study area, we broke it down like that so that we have classes of shape, whether it was a rounded ridge or upper slope or toe slope, occurring either at the highest elevation or the lowest, and in between. And then we have categories of slope. Again, I had to sit down with the geomorphologists and come up with these intervals, with the observe for 15, 28, etc. Does this make sense in terms of the geomorphology as well as the biological response? That's just a picture showing in the northern Rocky Mountains what some enduring features would be. Colder Peruvian slope, a warmer, relatively chill veneer slope, a colder, deeper chill slope on length overall. That's the sort of thing that was mapped by this model. Or the sorts of units that the model developed and then were mapped. So that's what the Muskwa-Kechika enduring features map looks like. This map here we show in more detail. This blows it up around Stone Mountain Provincial Park. It just shows from the units we're talking about, mapping, for example, high elevation, warmer steep slope on carbonate bedrock, for example. Now that's not just a geological map or a physiographic map. It's sort of a ecologist map of physical features. Makes sense to an ecologist, at least if you think about it. And that's a legend. That's an example of an Atlin-Taku portion of the landscape with a landscape image, and then enduring features view of that. So the two worlds are not completely separate. You can see where there's some common elements. And what are you going to do with this information? It's a pile of information, I'll tell you. And it's built up from 90 meter resolution pixels. There's a lot of agglomeration that goes on. Well, one thing you can do is, and that we tried in both areas, were to depict those parts of the study areas that had the highest physical variety or enduring variety, and those that were lower. So the darker colors show concentrations of enduring variety. In Muskwa-Kechika, they tended to be in the most mountainous areas for obvious reasons, because of topography. And the basin, like the Art Basin up around Watson Lake, has relatively low enduring variety. There's not a whole lot going on in that landscape physically. It doesn't compare to the mountains. And in some areas, like up here, there's a lot of serpentine and other kinds of bedrock. So even though the mountains aren't as rugged up there, they still have high enduring variety. And then you can do things like show where how that is captured by existing protected areas, or how well that enduring variety is represented by existing protected areas. That's Muskwa-Kechika. And there's a good chunk of it that's protected in the Muskwa region. One of them up here towards the Horse Ranch Range. You can also use it for fine filter analysis. So there are so-called special elements that are largely based on physical features. You want to mention some of them. It could be bedrock geology, like serpentine and karst, and canyons and cliffs, physiographic engines. There are some that are related to glacial history, like the glacial fluvial landforms in the western glacial refugia. And by the way, don't forget cryptic refugia. I mean, Linkages massive and obvious, but there's some evidence from DNA work now that east of the Coast Mountains in northern BC, like between Dease Lake and Atlin, there's some areas that may not have been covered by Pleistocene ice. And they found evidence for that in some alpine plants and also mountains. And there are process special features like landslides, hoodoos and dunes, rock glaciers, and then some unusual ecosystems like mineral springs, lakes with really open water, if you want to mention that. Concentrated spawning areas and underwater dunes. Those are communities or ecosystems, but they have a major component of enduring features. Now, when we were presenting this to the members of the Muskwa-Kechika advisory board, or whatever it is, management team, one of the fellows who knew the country said, well, that's all very well. There's lots of we show lots of enduring variety in the Muskwa ranges, but biologically, they're not that great. You've got a lot of rock and ice, and there's much more life farther east out in the foothills, Rocky Mountain foothills. Which is true, he was absolutely right. But thinking ahead, the Rocky Mountain foothills are probably going to suffer or have more negative impacts from climate change, more upheaval than the Muskwa ranges, which are it's a big chunk of high elevation terrain, and there's almost like internal resistance to change, and change probably won't be as fast. Moreover, as the livable envelope moves up slope, it flows more and more of the physical landscape to colonization. But also there's this idea that the elevational compression environment can result in mountains being good places for biodiversity in the broad sense. And obviously, moving uphill 100 meters is a lot shorter vertically than moving 1 degree of latitude horizontally. That is almost the metric for mountainous areas. But of course, it's not just about mountainous areas and enduring variety. The lowlands are also important in conservation planning, often of paramount importance, because they have the high primary productivity. They have more biomass, and they often have more of the species that people are interested in, like moose. Well, where could they be? Well, you can use growing degree days as a surrogate for primary productivity, as well as just landscape position, valley bottoms, low elevation valley bottoms, and some of the large wetland complexes are going to have higher primary productivity than higher elevations. And when I talk about growing degree days, I mean the amount of heat that's available for plants to use during the growing season. You can take a measure like growing degree days above 5 degrees centigrade. Means that plants can use it for cranking it down. And the models predict increases in growing degree days. And here we just mapped out those areas that presently have more than 800 growing degree days annually. And they're valley bottoms, the Rocky Mountain Trench, and a big area in the water basin. So the Water Basin may not have a lot of physical variety, but it has relatively high primary productivity. Yeah, that's a map showing the projected increase in growing degree days to around 2050. So Fort Nelson becomes an agricultural hotspot. And warms up a lot. This confounding fact, of course, Fort Nelson, you're not going to be growing corn there, partly because at present there's big areas of muskeg underlain by permafrost. One thing that the communities were able to relate to, all of them that we've dealt with, is changing alpine. So one of our projections is that there will be dwindling alpine zone throughout the region. And because these local people recreate, hunt, spend a lot of time in the bush, and a lot of it in the alpine zone. They're acutely sensitive or aware of what that could mean. And the metric we used was that projected increase in 3 degrees centigrade puts quite a bit of the existing alpine zone into the temperature range of the current sub-alpine zone, which translates to the 400 to 500 meter upward shift in the climate envelope. So, in a lot of places, the alpine zone shrinks where the mountains are not so extensive. It blinks out. And this isn't to say that the subalpine zone is going to migrate upward quickly and become subalpine forest. More likely, it'll be the shrubbery, the dreaded buckbrush, Arctic birch, and willows, probably more so than conifers, sort of a creeping lignification of the lower alpine zone. But the local communities are able to relate to that. And then you can do things like showing where the percentages of alpine loss are by physiographic problems. And almost all of it is lost from the Yard Plateau. You might say, well, that's not a big deal. There wasn't that much to begin with, which is true. Also, the Yard Plateau is ruined, and connectivity space or linkage space between the Mackenzie Mountains, Yukon and Northwest Territories, and the Rocky Mountains, northern BC. Things like caribou, you've got to have some high elevation to get across, or they may have to. John Weaver's work has demonstrated that use of that connection. Well, in Muskwa-Kechika, we also got into connectivity, considerations of connectivity. And I got to admit, I don't know how Carlos does this. Carlos Carroll. But he creates essentially a wiring diagram or a circuit board that shows movement pathways, or in this case, caribou, and then splodges, red splodges that are, he calls gateways of movement, where movement is a lot of lines of movement come together, and there are certain areas that he considers to be gateways. As I say, I don't really understand how he does it, but there's a really good Issues in Ecology, number 16, goes into some of these models. Explains them quite well. So we did that for some of the focal species, and then this is what it looks like for oats, sheep, caribou, and goose. Which use this landscape differently. The sheep and the goats are more complementary. Well, then we thought, well, could we in any way come up with some projection of ecological upheaval that would show that there'll be more upheaval in different parts of the study area. I like to call it upheaval because it's sort of a non-judgmental word. The consequences, some will be good, some not so good, some bad. But it's Earth in upheaval. I had to go into the climatic data that we had for the characterization of the ecological zones that we've been classifying for decades in British Columbia. So basically we've got the contemporary climate envelope for the montane, subalpine zones from north to south. And so I used the so-called baseline climatic data for temperature, mean annual temperature, mean annual precipitation, and growing degree data. And then a projection to 2050 for what it was projected to be. And basically tallied the intervals of temperature, precipitation, and growing degree days that would be crossed within each of the physiographic units. By that I mean, say, a projection of increased precipitation. In this case, a lot of precipitation is going to increase. If it went from 400 millimeters to 750, that crossed 2 or 3 intervals of precipitation. And so I did that for each of the 3 climatic parameters and tallied them up. And then we took a look at how that played out by physiographic unit across the region. And it indicated that the most change for upheaval was going to be at the lowest elevations, kind of especially in the Rocky Mountain Range, and especially in the Rocky Mountain foothills. Perhaps because those foothills in the rear of the big mountains are already relatively warm. They're getting warm and dry, and they're getting the air masses plunging over the mountains already kind of warm. And wouldn't take much increase in temperature and precipitation to push it into some rather different states. Anyway, that was our projected degree of upheaval map, and then we did things like overlay the caribou connectivity modeling with the projected upheaval, and in this case you can see the places maybe to watch out for, or where there were some red flags at the top end of the Rocky Mountain Trench. It opens up in the Yard Basin. You want to ask yourself, what does this mean for caribou? What happens if mountain pine beetle moves into it and kills the lodgepole plant? And on the Rocky Mountain foothills, which apparently the caribou spend a lot of time moving back and forth.
Interestingly, from way back to the corner of the Rocky Mountain, pretty much emulates the setting of that.
Oh yeah, it's just coming. Okay. And by the way, Horse Ranch Range is one of the places with relatively lower potential ecological upheaval and high enduring variety. And thank goodness it became a protected area recently. The Kechika First Nation were very keen on it as one of their sacred areas. So we didn't just play around with enduring features. We also tried to incorporate considerations of connectivity, and not just within the region, but beyond, whether it was transboundary rivers or connections from Muskwa to the Canadian Mountains, along the Liard River to the Alberta Plateau. And elevational connectivity as well as horizontal. I like to think about salmon. partly because it forces me out of my comfort envelope. I don't know much about fish, but it's a really good example of what G.E. Hutchinson called the ecological theater and the evolutionary play. There's been some really interesting work done on the Bristol Bay sockeye, talking about the portfolio approach, what they call biocomplexity, diverse life history strategies in geographic locations, and I especially like this one. Think of salmon landscapes as heterogeneous filters of climate. The regional diversity of population responses appears to derive from local adaptation of salmon populations to heterogeneity in landform and hydrologic conditions. So these enduring features have an impact not just on the terrestrial realm, but also the aquatic. I'm almost done. Don't forget, don't be mesmerized by climate change. Land uses are at work as we speak. And this is my last slide. This is for another talk, another workshop about cumulative effects in northwestern BC. This is me, not you. I mean, Seinfeld. I concluded that if they wanted to really deal with cumulative effects, they needed a regional environmental assessment, which you've done here, right? The stage of it. I wanted to know more about the historical abundance of purple species. Not so much to make me read, but more to try and understand what it was that produced way more species of large, numbers of large mammals and fish, things like that, in pre-gold rush times. And I have a different view of the impact of linear access on an intact landscape that, say, man has. The way I think of it is the first road, the first alpha incursion, whether it's Klondike or other gold rush or Alaska Highway or Highway 27 or railroad. The first one into the impact area has a big impact on the probability of maintaining ecological containment of the reservoir column. And that various more roads, especially roads, increase in sort of the depth 5,000 foot until you reach some threshold in that dive. I wanted to know more about freshwater ecological drainage units, the basin characteristics of all major rivers. The conservation units of salmonids, I mean genetic architecture. Groundwater dependent ecosystems. What are they and what are the threats? Regional natural capital ecosystem. More social services, social research. That looks like a afterthought, but not really. What I'm getting at there is we need more research into how people think, how local people assess risk, how they make decisions, and what community health and well-being means. All right, that's it, man.
Everyone, let me